Okay, so I want to show you a trick to show you how to make this thing somewhat easier to manage. Okay, so trick for such situations is what I'll call symmetrization. Okay. So what's that trick? So I'm gonna make a claim, which I'm not gonna justify. You can look it up if you want. So fact. This is known as Minkowski's inequality. Is that if you look at define for a random variable. So x is a random variable. Define for a random variable x. The p norm of x is the expectation of the absolute value of x to the p to the 1 over p. Okay. This is a norm. It obeys the things you usually expect, like the norm of ax, the norm of a scalar times x is the scalar times the norm of x. It satisfies triangle inequality, etc. So we really want to bound. Oh, and then one other fact that I want to state is called Jensen's inequality. And it says if a function is convex, then f of the expectation of x is at most the expectation of f of x. Oh, this is a norm, I should say, for p at least 1. So the trick that makes computing things like this a little bit easier is, well, this is the same thing as the 6 norm raised to the 6th power. So let's just bound the 6 norm. And then whatever answer you get at the end, you'll raise it to the 6th power. So you'll say, look, so I have the sum over I xi minus the expectation of sum over I xi. OK. And you might as well imagine that. So this is just a number. This expectation is just a number. So you might as well imagine that these xi's inside this expectation are independent copies of the actual xi's. So xi prime is a random variable that's independent of xi, but is distributed exactly the same way. So you get the same thing. Right? This is the same number. And then, you could. Let's write this suggestively as, I'm just rewriting where the x is. So this is the expectation of over the x primes now of sum over I xi minus xi prime. And raising something to the 6th power is a convex function. Or in general, taking the absolute value and raising to the p for p at least 1 is a convex function. So I can pull this expectation outside. So this is the 6 norm over this random variable, but this is at most the 6 norm over both random variables. Okay. So if this isn't clear, this here means expectation over the x's of expectation over the x primes, sum over I xi minus xi prime to the 6th to the 1 over 6th. But taking something and raising it to the 6th power is a convex function. So I can pull this expectation outside. This here can go outside. And it only gets bigger. That's Jensen's inequality. So that's what I did here. So this randomness, this norm is over both x and x prime are both random. And now these are independent symmetric random variables. So this is exactly the same distribution as putting in random signs. These are independent random signs. So I should have said this is Jensen. And now I use the fact that the 6 norm is a norm. So this is at most 2 times the sum over I sigma I xi. OK, so what we've just shown is that the original 6th moment that we wanted to bound is bounded up to this 2 to the 6th power, raise everything to the 6th, and then you get the 6th moment. The 6th moment is at most 2 to the 6th times the 6th moment of this random variable, which is a symmetrized version of the original one. So this is a mean 0 random variable now. All these sigma i's, all these guys here are symmetric random variables. And what's the point of that? So with the 6th power, and things don't get really that, well, 6th power is already kind of annoying, but especially if you go to really high powers, it gets really annoying. But symmetrization makes things slightly easier because let's look at this now. The expectation, remember, what is xi? Xi I define to be this thing here. So in particular, xi is equal to 1 with probability 1/2. Not 1/2, what am I saying? The size of I over m, which is, let's say, k over 2n. Right? What's the probability you land in an interval? You hash to an interval of length k in an array of size m. It's this. And it's equals 0 otherwise. So let me just call this, number p. Yeah. Yeah.
Where are the expected values exactly?
So, OK, so this really means this.
Yeah.
This means I took this outside. So it's an expectation over both.
OK, there's an expectation over both on the outside of that.
Yeah, so this thing here is the expectation over x and x prime of that thing to the 6th to the 106th. This is this. Does that answer your question?
Oh, okay.
So now if you want to bound the expectation of sum over I sigma I xi to the 6th, you'll expand this out and you'll get a sum over I1, I2, up to I6 of the expectation of a bunch of sigma powers, sigma I1, sigma I2, sigma I6, times the expectation of xi1, xi6. OK? And the point here now is, what is the expectation of this thing here? What is this expectation? I claim the expectation has one of 2 possible values. 0, 1. And when is it 0? When is it 1? That will certainly make it 1, but that's not the only time it will be 1. Yes. Every one of these indices I, so there's I1 up to I6, it should appear, some of these i's might equal each other, right? But if you look at the distinct i's that appear here, each one should appear an even number of times. OK? So the situations are all appear twice, or one appears 6 times, one appears 4, and one appears 2 times. I think those are the only situations. OK? And let's say that they're all the same. One appears 6 times. Then this thing here is just xi to the 6th, which is the same as xi, because xi is only 0 or 1. And so that gives you p. OK? Or if all of them appear, if there's 3 guys appearing twice each, then you'll get p cubed here. Okay. And then you also have to take into consideration the choices of all these i's. So how many ways are there to choose 3 guys to appear twice each? It's like n cubed times some coefficient. So the bottom line is kind of the dominant term is the case where this is dominated by 3 distinct items. What you would find, 3 distinct items appearing twice each. And that gives, well, there are n cubed choices of those 3 items, or n choose 3 choices. And then you have to take into consideration the permutations that all give the same thing. So there are n cubed choices, and then you get p cubed. That gives O of n cubed p cubed. Okay.